Thank you for joining us for another amazing show. We have a fantastic guest lined up for today. His team is really deeply embedded in helping companies get to orbit faster and smarter while also extending payload opportunities in by using in-space assembly. Welcome to the Tech and Space Leader Show, where we learn lessons from leaders of the next frontier. I am your host, Lisa Dreher, and I'm really excited to introduce our guest for today, Joe Landon. He is the co-founder and president of Rendezvous Robotics. Welcome to the show, Joe.
Thanks, Lisa. It's great to be here.
Absolutely. Maybe we can start by having you give a little bit of background on yourself and Rendezvous Robotics.
Sure, thanks. And again, thanks again for the opportunity here. My name is Joe Landon. I'm the co-founder of Rendezvous Robotics. My background, I've been in the space sector my whole career. I've been working at both big companies and small companies over that time, and co-founded Rendezvous Robotics about a year and a half ago. And we're focused on building spacecraft that are more capable than can be folded up to fit into a rocket. Simply put.
Yeah, that is amazing. So, how did you really initially come up with this concept of self-assembling spacecraft? And what problem is that really trying to solve?
Sure. So Rendezvous Robotics, I've got two other co-founders, and one of them is Dr. Ariel Ekblaw, who has spent a lot of time at MIT developing and inventing self-assembly technology for spacecraft. So that's really where the idea started many years ago at MIT in the lab on how do we build larger, more capable structures in space using self-assembly. And Ariel's initial focus was on how to build habitats because we want to be able to launch in a really small, compact configuration and then build a really big enclosed volume to build habitat. So that's where the idea started. And when me and our third co-founder Phil Frank got together, we looked at the technology to assemble things in space, and we said, well, actually, there's some other really interesting opportunities and needs right now to build just spacecraft that are more capable. Like I said, higher power and more capable spacecraft that today we're kind of reaching the limit of this sort of complicated mechanical origami folding that we do to fit spacecraft into a rocket. So that's what really we're set out to solve. And the way we do it is we build spacecraft in modular pieces, flat tiles that launch to space in a dense stack, and then autonomously self-assemble using electromagnets once they get into orbit.
Oh my gosh. Okay, so this is amazing. And I guess the whole idea behind this is to really be able to launch, I guess, more capable spacecraft and larger spacecraft, but without having to, I don't know, completely limit the payload size. Is
Right.
that kind of the concept?
Yeah, today we're limited by what we can fit into that rocket fairing, and the rocket fairing is kind of cylindrical, volume, right? So if you think about the things we launch into space today, satellites have big solar arrays, big antennas, and are going to need big radiators. All three of those subsystems, performance is driven by surface area. So in order to really achieve that surface area in space, we're going to need to break through that constraint of the fairing and be able to assemble things in space instead. And we've achieved that so far by doing this origami folding and mechanical deployment systems. And that's what we're going to make. We're going to replace that with in-space assembly.
Wow, amazing. Okay, when in terms of technical breakthroughs,
Mhm.
what does this mean from an autonomous in-space assembly perspective? How does that become achievable?
Yeah, so I think what we benefit from a couple technical advances, primarily advanced computing, the ability to put more computing power and autonomy into a smaller footprint and lower power, and also the supply chain for small spacecraft components. So we're able to miniaturize things. Like everybody pretty much benefits from that in the space sector. And then we're developing new technology to use electromagnets and sensors on the parts of the spacecraft itself to control and move those parts into the final configuration once it's in orbit. So they get into space as a flat, dense stack and then shape shift using electromagnetic control into the final form.
It still sounds a little bit like sci-fi
Yeah.
type of thing. So, how close are you to actually having something that can launch and assemble?
Yeah, so we actually have made a lot of progress on proving the feasibility of this, and Dr. Ekblaw at MIT and later has launched this self-assembling technology to space 3 times. So smaller, less capable prototypes have flown to on New Shepard and to the International Space Station twice. And we have a 32 tile experiment flying to the ISS with the ISS National Lab coming up here later this year. So we'll show that we can do within the confines of the ISS a complex 3-dimensional self-assembly using this magnetic approach. And then what we're working on now is following up on that mission. Next year, we're going to launch 7 larger, more capable tiles and be the first to assemble a full spacecraft in LEO.
Oh my gosh, that's really exciting. What types of missions or platforms does this really support in terms of being able to expand or reconfigure once on orbit?
Yeah, so I mean, really, from a capability standpoint, the types of missions, it's almost like almost everything will benefit from this in space, but there's some specific ones that will really benefit soonest. So communications missions need large antenna apertures, and we're uniquely able to assemble those antenna apertures in space without having to do the origami folding. So I used to work on large geosynchronous commercial communication satellites, and we would build these complicated sort of unfolding antenna arrays, and the biggest that we can do today is about 20 meters in diameter. And it's just not big enough. It's not even that big, if you think about it. So we can build, antennas the size of football fields or really unlimited scale by not having to do that folding and by sending the parts to space and assembling it there instead. So communications missions for sure. And then also remote sensing missions, particularly ones that use RF remote sensing or missions that need high power or have high heat dissipation. So like radar missions, missions that need a lot of in-space compute capacity, so are generating a lot of heat. We can assemble radiators in space that dissipate that power more effectively. So things like direct-to-device communications, compute in space and data centers, military communications missions, all of these will benefit from that next sort of level of performance that we're not able to do today.
Yeah, yeah. You spoke a little bit earlier about how this concept really addresses some of the limitations of the launch vehicles themselves. What other new missions will become possible when this is available?
Yeah, I think the really taking some of the missions we're used to, like I said, remote sensing and communications, and being able to make it more possible to do higher performance. So, and also, really looking at, we'll be able to influence the economics of space that make new business models possible as well. So, really, we do that in 2 ways. One is by making launch more efficient because we can launch more capability per launch than you can today. So if you look at a satellite when it's inside the fairing, there's lots of empty space because we have all these systems that have to fold up and fit in. We can fill that launch fairing, whichever rocket it is, full with tiles to the exact, use all that volume very efficiently. So we'll get more capability per launch. And then once you have a modular spacecraft, it actually is inherently repairable, upgradable, and changeable because we can reconfigure those modules once they're in space. So that changes to the economics of space missions as well.
So talk about that a little bit more in terms of the reconfiguration capability. What does this mean from the ability for companies, commercial space companies, and perhaps
Mhm.
other governments to scale and have redundancy and sort of that long-term value of that spacecraft?
Yeah, and this is beyond just fitting more stuff into a fairing. The modular spacecraft that we're building really are going to change how people think about space missions. And right now, we build a satellite on Earth, and it's done. It's in its final form. Then we fold it up to fit into a rocket and then unfold it in space. And then as soon as the first thing goes wrong or runs out of life on that satellite, we throw the whole thing away. What we can do if that spacecraft was built from modular tiles by Rendezvous Robotics, we can keep some of the things up there, like the structure, the solar arrays, the radiators. There are things on a satellite that last longer than the current lifetime of some of the payload components, let's say. So what if you could, instead of throwing your whole satellite away and building a new one and launching a new one, you could just replace the parts that need to be replaced? We can enable that with modular spacecraft, built from these modular pieces that self-assemble and are able to reconfigure later.
Wow, this must really influence or impact the economics because like if we're today throwing so much of these
Mhm.
spacecraft as a whole away and now we don't have to, how's that really, I mean, that's going to have a huge impact on the
Yeah,
economics.
absolutely. I think that's right. And building on what I said before, not having to throw away that whole satellite every time and be able to instead launch the part or the computer or the sensor that you need really changes the economics. So you're not rebuilding, throwing away and rebuilding stuff that's working just fine. The other way is that we could think about space missions sort of in a different temporal way, where we can have our modular tiles in space, and each tile could have, there could be different types, like it could be an antenna tile, a solar array tile, a compute tile, and we can even stage those in space. And when you need a mission, you can say, okay, I'll take 10 solar tiles, 2 compute tiles, and 3 radiator tiles, and then do your mission. And then when you're done, just put them back in storage and wait. The next person can use them for some other purpose later. So that's really different, and doesn't even require all this sort of build, launch, throw away cycle that we have today.
That's, that is amazing. That is a completely different way of thinking about the way we operate in space. What level of autonomy, though, is required in order to make this possible?
Yeah, I think the ability to self-assemble is an autonomous process, and that's what at Rendezvous Robotics, what we're doing is making the parts of the spacecraft a little more capable so they can assemble themselves. So looking at how we have built stuff in the past, we've had humans with wrenches assembling things, like the space station. It's not very scalable, and there's a lot of reasons why you don't want to do that. Or there's a robotic arm or a robot of some kind that's human operated or human supervised, which is also not scalable. So what our system does is a level of autonomy where the system builds itself, the satellite builds itself. You don't have a robot or a robotic arm left over when you're done, and those tiles can assemble and then they latch together into a rigid structure once they're in space. So um, it's much more scalable and autonomous in that it's more of a swarm self-assembly process versus today, where it's like, okay, my robotic arm, I have to plan out every movement of that arm.
Right, right, right. I'm sure, though, that there are still some significant engineering challenges associated
Huh.
with the precision rendezvous and robotic assembly in space.
Hmm.
Where are you at on that? And I mean, you've kind of talked about previous missions,
Yep.
and it sounds like there's new missions coming up. How much is left here to make this a reality?
Yeah, we've come a really long way already with the technology, proven that magnetic self-assembly is feasible in zero gravity. And some of the challenges that we're working on now is that precise and control in sort of three-dimensional space using magnets. So you can have control of one spacecraft, one part of the spacecraft, and the other, recognize each other, understand how they're positioned and where they need to be in order to be assembled. So that requires really precise control of electromagnets and manipulating magnetic fields. And that's really our work that we're doing now. And we'll demonstrate that next year in our LEO assembly mission.
Wow. Oh my gosh. Really, really exciting. I'm imagining also that this really impacts this whole issue that we have with space debris if we can reuse some of these elements. How also, is there an aspect to what you're doing that could, I guess, support that?
Yeah, I think any having our spacecraft that are modular and reconfigurable could inherently be less debris generating because we can use things for longer, so we don't have to send out more things to replace the stuff that we're deorbiting. So that's good. I think that's also one of the challenges is that we're launching a spacecraft that starts its life as a stack of tiles, which are all separate and not connected, and then assemble in space. So there's some education we have to do in the market to be able to do that successfully and safely. And that's certainly one of the things that we're priority for us to ensure that our system is very reliable and repeatable, so that we can do that assembly um, effectively.
Yeah, absolutely, absolutely. Well, Joe, I want to thank you so much for being here today. If someone wanted to learn more about Rendezvous Robotics, what should they do?
Yeah, sure. So we've got a, website and LinkedIn and presence online, or reach out to me directly. We'd love to talk about what we could do for your mission and how a modular self-assembled spacecraft could outperform what you can fold up to fit in a rocket.
Fantastic. And I do want to take a moment to thank GuideForce for hosting these sessions. To learn more about GuideForce, you can visit guideforce.com. And we'll see you next time on the Tech and Space Leaders Show.